Everybody. In this video lesson, we're going to analyze the motion of charged particles in an electric field. So that will be electric fields where the field strength varies depending on how far you are away from a big point charge. We'll also look at the motion of charged particles in a uniform electric field between two parallel plates. So let's get started. So to start, think about a small positive charge, so Q1, with a very small mass in a vacuum distance of r from a fixed charge Q2. So when we say fixed charge, that means it's not going to move. So you can imagine two positive charges want to repel each other. Excuse me. Well, in this scenario, if we were to release Q1 and Q2, Q1 would move away from Q2. But since Q1 is fixed, it's going to stay where it is. So Q1 would experience an electric force or a Coulomb force to the right. And the magnitude of that force, well, we know how to calculate that. Did that in an earlier lesson. K Q1 Q2 over r squared. So if that charge mass Q1 is free to move, it's going to accelerate. And it's going to accelerate in the direction of this electric force. And that's just Newton's second law, right? Force equals mass times acceleration. And the instantaneous acceleration, well, since F equals ma, at any time, the acceleration is going to equal the electric force divided by the mass of the charged particle. So if we want to analyze this object's motion, why can't we use our standard kinematics equations to get the motion of Q1? So if you want to think about that for a moment, have a sip of coffee. You can unpause when you think you have the idea. So the idea is, as Q1 moves farther away from Q2, its R is changing. As R increases, the electric force is going to decrease. And as that electric force decreases, the acceleration is going to decrease. So yeah, M is going to be accelerating, but its acceleration will not be uniform. It won't be constant acceleration since A changes as F changes. So in scenarios like these, involving like point charges, we won't be able to use our kinematics equations to analyze the motion. But all is not lost. We have other ways to analyze motion too. Conservation energy helps us analyze the motion. So we're going to use conservation energy techniques. So if we neglect gravity, which as we've talked about, is usually not a big deal because electric forces are generally so much bigger. And also if we're talking about a horizontal problem, there is really no change in gravitational potential energy. And there's no springs, so no spring energy either. But in this case, the total energy of the system is we have electric potential energy between the charges, and then that's being converted to kinetic energy. So we'll do a little derivation here. So the energy before they were released equals the energy after. So what is the energy before? Well, in this question, we're purely talking about electric potential energy and kinetic energy. Whoops, equals EK2 plus EE2. And if we do a bit of rearranging here, if I bring the, I'm going to bring, which one do I want to bring over? I'll bring over the electric potential energy. So if I group the potential energy, electric potential energies on the right, and group the kinetic energies on the left, notice on the right, this is the change EK2 minus EK1. That's a change in kinetic energy. EE1 minus EE2 is the negative of the change in electric potential energy. So what this is saying is that EPE lost gets converted into kinetic energy gained. And this scenario is not unlike lifting some object in the air and letting it drop. All that stored gravitational potential energy, when you drop it, gets converted to kinetic energy as it falls. It's kind of a similar case here. You bring two like charges together and store some energy, and when you release them and they're free to move, that stored energy gets released as kinetic energy. And so that's going to be kind of the starting point for our problem. So the total energy between the charges is constant, and lost electric potential energy gets converted into kinetic energy. So that's the key idea that I have there on your sheet, guys. And we're going to use this idea to solve a couple of problems and then look at some parallel plates. So let's do a problem together. So we have two positively charged particles, and one is fixed. So in the diagram here, this 4 microcoulomb charge, this guy is fixed. It is not going to move. But we have a second charge here that has a charge of 8 microcoulombs, and this one is free to move. So if you can imagine, once the system is released, this guy is going to move to the right. This guy here is going to stay fixed. He's going to stay there. So again, these problems, when you see fixed, that's what it means. Only this guy here is free to move. In this diagram, these arrows are just indicating the distance between them initially is 0.5 meters. So what we're interested in asking is, so once we release the system, this guy here is going to move to the right, and as we talked about, that we're going to lose electric potential energy. This guy is going to gain some kinetic energy, and we want to know, after it's moved 0.5 meters, how much kinetic energy has it gained, i.e. what's its new speed. So we're going to do this using our conservation of energy techniques. So here we go. So you can set this one up using negative delta EE equals EK. Or if you just like the classic, if you just feel good doing EK1 plus EE1, like that's fine too. Equals EK2 plus EE2. Now, initially, both charged particles are being held and they're at rest, so we have no kinetic energy. We do have some electric potential energy, and it's given by K, Q1, Q2 over R1. They're kind of initial distance apart. And then when the second the second charge is moved another 0.5 meters, so it's a new distance away. They have the same charges, but they're at some new distance. Oh, actually, that's the kinetic energy. So that's the electric potential energy. Just mix up that order. And then the second mass is obviously going to have some kinetic energy. So 1/2 m, and I'll use V2 squared since that's what's on the diagram. So this is the scenario, and I hope you guys would agree. We know the distances, we know the charges. We can find these electric potential energies. We know the mass, we can solve for V2. So at this point, it's what do you prefer to do? Do you like to plug in and do the numbers right away? Or do you like to solve for things in a general sense? And you guys know me. I'd rather do things in a general sense. So I'm going to imagine I'm going to move this term over, K Q1 Q2 over R squared, or over R2, because then I have a lot of things in common between those two terms. Both of those terms have a K Q1 Q2, and what we just have is 1 over R1, and then we'll have minus 1 over R2. So that's just going to cut calculations down. It was 1/2 m V2 squared. And then I can see how to get V2 by itself. So I know I'll be square rooting in the end. And I'm going to multiply up my 2 and divide by my m. So I have 2 K Q1 Q2 divided by the mass, and then times 1 over R1 minus 1 over R2. So I'm going to do that and plug everything in right away and just get V2. Of course, if you had plugged stuff in right away and just worked it out, it would be the same thing. So 9 times 10 to the 9. Q1 is 4 microcoulombs. So micro, 10 to the minus 6. and then 8 times 10 to the minus 6. We're dealing with energy here, so the signs matter, but they're both positive charges. Mass, 250 grams, so 0.25. And then R1 was 0.5 meters. R2, the distance they are apart, remember, so that'd be 0.5 plus 0.5, so they're 1 meter apart in the end. Whoa, what's happening to my thing there? That was crazy. This bracket here, actually, 1 divided by 0.5 is actually 2, and 2 minus 1 is just 1. So that whole thing just actually equals 1, just to make calculations simpler. So 2 times 9x9 minus 4x minus 6 is 8x minus 6 divided by 0.25. That seems like a rather large speed. So I'm going to try that again. I got like 20,000 meters per second. Times 4 times 10 to the minus 6 times 8 10 to the minus 6 equals, yeah. This seems a lot more reasonable. About 1.5 meters per second. Seems a lot better. I bet for a lot of you guys, especially after the lesson on electric potential, it's nice just to do some kind of straightforward conservation of energy problems. But yeah, so we're now just mixing in electric potential energy into the mix. We understand if we have two particles that have the same charge, when they're free to move, they're going to repel each other. They're going to start to move. We can use conservation of energy techniques to analyze that motion and find the speed at certain points. So if you'd like to pause the video actually and try this one yourself, you can, or you can follow on with me if you want to as well. So I'm just going to diagram this one out. So we have two positive charged particles. They are 25 centimeters apart, so 0.25 meters. And in this question, this one's a bit different than the previous one. They're both free to move. So afterwards, after some time, when we're told, so they're both, when they're released, one will move right, the other move left, right? And initially they were 25 centimeters apart. And we're told that when they're 75 centimeters apart, they're each moving with the speed of 100 meters per second. And so this symmetry makes sense because they have, this question says they are identical positive charges. So they have the same Q. And we want to determine, well, what is that charge that would give them this speed a certain distance away? So I'm going to set it up the classic way that I like to do it. Again, negative delta EE equals delta EK would be a totally fine way to start this problem. But remember, that's just equivalent to what I'm writing down here. And I think, at least from my experience, most students just find a comfort level and just like, here's all my type of energies, and then here's what's zero, and it just feels better. So they're initially at rest, right? So EK1 is 0. And so what's EE1? Well, it's K, and then we have the unknown charge Q, but they're identical, right? So I'll put Q squared and divided by R1. And then KQ squared, and they're at some new position, R2. And then if we are a bit clever about this, we can, actually, yeah, let's just be clever about it. We have two of these particles moving with a kinetic energy of 1/2 mv squared, because they're identical particles, right? So they have the same mass. Did we get the mass with this one? Yeah, 100 grams. And so they're both moving at that speed, so multiply by 2. And then we have everything we need, guys. So we can solve, we should be able to solve. So that's 2 over a half is 1. So we know M, we know V. Yeah, we should be able to solve for Q. I'm going to do kind of a similar thing to what I did last time. So if I bring KQ squared over R2 over, I get KQ squared, and I have 1 over R1 minus 1 over R2. And on the right, I just have MV squared. This makes it easier to get Q by itself. So to get Q by itself, I'm going to take MV squared, and I'll divide by K, and 1 over R1 minus 1 over R2. And that's just going to spit out my value for Q. So let's do it. As usual, if you prefer just to plug in things ahead of time, that's totally okay too. So M, 100 grams, 0.1 kilograms, 100 meters per second squared, 100 squared. K, 9 times 10 to the 9. And then R1. So 1 over 0.25 minus 1 over 0.75. So if you want to take a moment and give that a go. I'm actually going to work on I'm actually going to do the bottom myself. So 1 divided by 0.25 is 4. 1 divided by 3/4 is 4/3. So this worked out to be like 2.6 repeated times 9 times 10 to the 9. And so I got my bottom first. And if I put that to the power of -1, and then I can multiply the top. So I'm just talking through my steps. Of course, you can calculate this in a couple steps if you want to. So I got 2.04, or just 2, but I'll say 2.04 times 10 to the -4 coulombs. And I know it's positive. They are positively charged particles. All right. Now, technically, when solving this step right here, a positive value or a negative value for Q would actually give the same answer. But our question said they were positively charged particles. So if my question said they were negatively charged particles, then I would take the negative of the square root. But yeah, so just a second example using conservation of energy to solve a problem. But in this case, we had point charges setting up an electric field. The force changed, the acceleration changed, so we need to conservation of energy techniques. What about when the force is constant? Within parallel plates, the motion is a bit more straightforward because the electric field strength is the same everywhere. The force is the same, the acceleration is the same. So what we're going to do next is we're actually going to get an expression for the acceleration of a charged particle inside parallel plates. So our starting point is this. So inside our parallel plate, Fe equals Q times epsilon. Now this is actually always true everywhere in electric fields, but with remember with parallel plates, this epsilon is constant, right? And the acceleration from Newton's second law is going to equal the force, because force equals mass times acceleration. So within two parallel plates, that acceleration is going to be whatever electric force the charge experiences divided by its mass. And electric force is just Q times epsilon divided by its mass. And again, this is constant acceleration because those three things, Q, epsilon, M, obviously Q and M are constant, but inside parallel plates, epsilon is constant too. And often we don't know the electric field for a parallel plate capacitor. What we know is its plate separation and the potential difference. And if you recall, we had an equation for that, right? Potential difference equals epsilon times R. And rearranging that, epsilon was potential difference divided by R, the plate separation. So now we have an expression. So inside, if we have some charged particle with a certain charge Q and mass M, and it's inside a parallel plate apparatus, a capacitor, with a certain plate separation r and a voltage delta v, we actually can just determine the acceleration. And because it's constant acceleration, we can use our kinematics equations to analyze the motion. Now, I have something else to do over here. There's a second way that we can analyze the motion within parallel plates. We can still use conservation of energy. That still works. But sometimes if you have constant acceleration, sometimes just using kinematics is good. Or we can use COE. And remember, the change in electric potential energy, the electric potential energy lost gets converted into kinetic energy. And we had an expression for electric potential energy. It was Q delta V. So if we are within two parallel plates, delta V is known, the charge on the particle is known, and we can analyze the motion that way too. So there's two approaches to it. And so we're going to do an example now, and we are going to use both methods and see that we get the same result. Now, one thing I want to mention before we begin is on the left here, remember Fe equals QE, that is in magnitude, right? These are all magnitudes, including the charge, right? On the right, with conservation of energy, the signs matter. So signs matter on the right, signs don't matter on the left. So keep that in mind as we do the next problem, because we're going to get to a solution where one of our methods has a positive and one has a negative. But remember, it's because when we're dealing with F equals Q epsilon, that's magnitudes. So yeah, we're not violating anything. So the example we're going to look at is an electron gun or cathode ray tubes. So this is basically how like our traditional maybe computer monitor or TV would work. More so back in the day. Like honestly, I'm not up to date on the new technologies and flat screens and whatnot, but these cathode ray tubes, it's essentially how we got images projected on screens. So what happens is we heat up an oscilloscope, and what basically it does is you can think of it frees some electrons. And if we have some free electrons, and we go from a region where, so if we get some free electrons in here, and we have a region of low potential, negative charge, to high potential, positive charge, well, what are those electrons going to want to do? They're going to want to repel from the cathode, the negative charge. They're going to want to move towards the anode, the positive charge. And in this electron gun, those electrons are kind of accelerated through this region from low potential to high potential, and then they're fired out as an electron beam. And then they hit some kind of fluorescent screen. And honestly, whatever they do is way above my pay grade here. But what we can actually do is, if we know the potential difference between the cathode and the anode, we can determine the final speed of the electron coming out of this cathode ray tube. So we're going to do that now, and we're going to use two methods. Yes, so I've got some screens to do that. So let's just chat about a couple things. So we are using an electron. So you can look this up. But the mass of an electron is 9.11, but we'll just use 9.1 times 10 to the minus 31 kilograms, so very tiny. And we have our potential difference. In this case, it's 20,000, or 2 times 10 to the 4 volts. We also know the charge, right? In this parallel plate apparatus, in this cathode ray tube, it's an electron, right? And we've already talked, we know the charge in electron. It's negative 1.602 times 10 to the minus 19. Now, something I might add here. If we look at the problem from an energy perspective, we would put in negative 1.602. If we are looking at the problem using F equals QE, that magnitude perspective, we'll put in positive. So I'll just put in plus or minus. It's going to depend on what we're doing. But hopefully that makes sense to you. And I've just explained my reason for adding a plus minus there. It just depends on what method we're going to use. So can I think I have the slide here, so I might as well use it. So let's use conservation of energy first. So from the setup from our previous slide, remember change in, I'll just even rederive this on this one. The change in electric potential energy gets converted to kinetic energy of the electron. And that change in electric potential energy is given by Q, the charge of the particle, times delta V, the potential difference, and that's going to equal 1/2 mv squared. So we assume the electrons are kind of released from rest, and they accelerate through the cathode ray tube. Think of it as like a parallel plate capacitor, a region of potential difference. They're going to come out with some speed v in the end. And we know all these things. We can solve for v. So v equals, so we're going to bring up the 2, so negative q delta v, divide by m, and we'll have to square root that. And because this is an energy problem, we're using q equals negative 1.6 times 10 to the minus 19. And by using that negative, everything checks out, right? We're not going to be rooting a negative number. We'll have a positive. So negative 2, 1.6 times 10 to the minus 19. Potential difference was 20,000. Mass of an electron, pretty small, was 9.1 times 10 to the minus 31. And we'll get our speed these electrons come flying out at. Oh, I plugged in, I forgot the negative here. So negative 1.2. Yeah, so that's going to give us a positive value. So we're dealing with really small numbers, but like check out the bottom. Remember when you're dividing by a very small number, you actually get a very big number. So by dividing by 9.1 times 10 to the minus 31, you get a huge number. And I know we're rooting that, but you wind up with a very, very big number. So you get about, excuse me, 8.4 times 10 to the 7 meters per second. And that is roughly, it was so big, I kind of just looked it up earlier. 28% the speed of light, which is pretty cool. Now, excuse me, later on, when we talk about relativity theory, we'll actually learn that things traveling that fast, we actually have to take relativity theory into account, but we're just going to ignore that for this problem. So pretty neat. We found the speed these electrons are flying out of this cathode ray tube at. Now I want to show you a second way we could do the problem, and I'm going to convince you that we would get the same answer. So we're going to use, in the second method, we're going to use our derived acceleration formula. So I'm not going to redo the derivation. You guys have it on your page there. We got that the acceleration was q delta v over mr. And this is constant acceleration because we're kind of inside a parallel plate capacitor here. At least that's the assumption. So if that's the expression for acceleration, our goal is to find v2, that v2 we're coming out of the electron beam with. And if we think about, we know that v1 equals 0. So I might just draw this over here. So the electrons are heated up. They come out. They're just kind of, they're freed. They're not moving. They're freed with a speed of 0 meters per second. And they come out. We want to know what the speed they come out with is. So if you know the final speed, the initial speed, a useful equation is this one. This will be our starting point. V2 equals V1 plus A delta D, 2A delta D. Now, if you're worried that, hey, there's two things we don't know in there, you are right, but check this out. So V1 is 0, gone. Look what we know for A. A is Q delta V divided by MR. But what's delta D here, right? Well, delta D is just the distance that the electron travels between the two parallel plates. So that's actually just the plate separation. So delta D we can replace as R, right? It's just the plate separation. And R divided by R, it divides out. And look what we have left. 2Q delta V divided by M. Sorry, that's V. That's if you've been screaming that I'm using the wrong equation, you're right. Because it's V2 squared equals V1 squared. And we're going to root this in the end. And this is the exact same, check it out. Like, this is the exact same formula we got before, right? Like, literally the exact same. We got one of those, we got this formula one way using conservation of energy, and we just got it a second way using the constant acceleration formula. So that's really awesome. And I mentioned earlier, we're going to have a difference in signs, but it's okay because this method, using energy, the signs matter. And so we plugged in Q as negative 1.6 times 10 to the minus 19, and it divided out. This method here remember that used F equals QE, epsilon, excuse me, which is magnitudes, which means Q is, we're looking for Q, it's the magnitude. And so here we were using positive. And so we will get the same, we will get V2 being, we won't be rooting a negative is what I'm trying to say. And we don't need to do the calculation, we already did it. But I personally, that's one of my favorite examples to do in the whole course. Just it's so interesting that we can analyze the problem from two different ways and come to the exact same equation. Yeah, I thought that was pretty neat. All right. That brings us to a close with our discussion, for the most part, on electric fields, forces, and electric potential. The last type of field we haven't discussed is our magnetic fields. So in our next day, we're going to review some important ideas from the grade 11 course. Specifically that, just the idea that a moving charge generates a magnetic field, but also a magnetic field can exert a force on a moving charge. And then we'll actually, in our next day, we'll just do a few derivations and actually quantify what the size of that magnetic force is. So it actually should be a bit of a lighter day, nice little break, time for you guys to catch up on things. But that's it for now. Guys, hope you're having a great day. Stay well, and we'll see you soon.